Today, we will talk about the Pitot static system, which is a system that feeds some of the basic flight instruments. The basic flight instruments are these 6 instruments that we will find in any aircraft, since they provide information about the most important parameters to consider when flying an airplane. Due to the fact that there are 6 instruments, and they are in this arrangement, they are sometimes referred to as the 6-pack. Here we can find the airspeed indicator, the attitude indicator, the altimeter, the turn coordinator, the heading indicator, and the vertical speed indicator. However, it is not enough just to know what information these instruments give us and how to interpret it, but also to know how they work, that is, their principle of operation. In this case, 3 of these instruments, specifically, the airspeed indicator, the altimeter, and the vertical speed indicator, use air pressure to give their readings. While on the other hand, the attitude indicator, the heading indicator and the turn coordinator rely on the gyroscopic principles to work. In this particular video, we are going to focus on the system that allows to measure the air pressure to power these 3 instruments, which is known as the Pitot static system. This system then measures the air pressure and provides the information to the relevant flight instruments. However, it is not that simple, since there are different types of air pressure. We have the static pressure, the dynamic pressure, and the total pressure. So in order to understand how the Pitot static system works, first we must see the definition of each of these pressures. Let's start with the static pressure. This is also known as the atmospheric pressure, and it is the pressure that the air exerts on the objects that are inside the atmosphere. This pressure is distributed evenly around all objects, as we can see in this image. And we must also say that this pressure is present at all times, regardless of whether the object is stationary or moving. Now, having seen these basic characteristics, we could ask ourselves, what does the static pressure depend on? Well, the atmospheric pressure, or static pressure, varies mainly with altitude, but let's see why. Here we have the surface, which in this case we are going to assume is at sea level. And here we have a column of air above it that spreads up into the atmosphere. As we can see, the air molecules are much closer together at the bottom, near the surface, while as we go up, they separate more and more. This has an explanation quite logical. Air is made of matter, and matter has weight, so the gravity of the Earth makes the column of air that is above us exert a certain weight, which causes the particles underneath to compress more and stay closer together. This weight that we feel from the air column that we have above is precisely the static pressure. And at sea level, this static pressure is approximately 30 inches of mercury. To be exact, under standard conditions this is 2992 inches of mercury, however this value may vary slightly depending on the weather conditions. In this order of ideas, as we climb in the atmosphere, we experience less static pressure. For example, if we climb a mountain, in this case the column of air that we have above is shorter. This means that there is less air exerting weight on us, and therefore the static pressure is reduced. In this example, in this part of the mountain we measure a pressure of 24 inches of mercury, which is obviously less than the pressure at sea level. Now, if we continue climbing the mountain, we can see that the static pressure decreases more and more. At the top, for example, we can measure a pressure of 15 inches of mercury just because we have less air above us. In general terms, we can say that the static pressure is reduced by 1 inch of mercury for every 1,000 feet of altitude increase. Which means that an aircraft flying at low altitudes will experience a higher static pressure than one that is flying higher. And this phenomenon not only occurs with air, but also with any other fluid, such as water. Here we have an example of a swimming pool. As we can observe, the way in which the water molecules behave is quite similar to air molecules in the atmosphere. This means that a person who is swimming on the surface will experience less static pressure than one who is swimming in the depth. And we can actually feel that change in the static pressure of the water as we submerge deeper, especially in the ears. Now, since we have seen and understood the definition of static pressure, let's move on to the dynamic pressure. This is the pressure that air exerts on an object moving through it. So when an object impacts the air at a certain speed, that air exerts a certain pressure on that object, which is called dynamic pressure. And this pressure is exerted in the opposite direction to the trajectory of the object, as we can see in this example. This dynamic pressure depends directly on the speed at which the aircraft is moving and also on the density of the air. Which means that as we fly faster, we will have a greater dynamic pressure and vice versa. For example, if we fly at 80 knots through the air, we will have less dynamic pressure than if we fly at 120 knots. Having already seen then the definition of dynamic pressure, let's now see the last one, which is the total pressure, also known as Pitot pressure. This corresponds to the sum of the static pressure plus the dynamic pressure. Let's see this through an example. Let's suppose we are traveling on the highway and put one hand out the window in such a way that the palm of the hand is exposed to airflow. In this case, the hand will experience two pressures. We have the static pressure that is always present regardless if we are moving or not. And we will also experience dynamic pressure due to the airflow against which we are moving. So in this case, in the palm of your hand you will experience the sums of both the static pressure and the dynamic pressure. And this is exactly what happens with an aircraft that is moving through the air. It will experience both pressures. Having already understood all these definitions, let's now see what the Pitot static system consists of. This, in its simplest form, is composed of a Pitot tube and a static port that feed the three instruments that we had mentioned previously. The static port sends information to the three instruments, the airspeed indicator, the altimeter, and the vertical speed indicator. While the Pitot tube only sends information to the airspeed indicator. We will now see each of these sensors more in detail, so let's start with the Pitot tube. This is a small tube that allows to measure the total pressure of the air as the plane moves through it. We can find it typically under the wings on small aircraft or in the front of the fuselage on larger aircraft. The idea of the Pitot tube is to measure precisely the pressure with which the air impacts the aircraft. And as we had already said with the example of the hand, the impact pressure will combine the static pressure and the dynamic pressure, meaning that the Pitot tube measures the total pressure. Now, in order to ensure that this Pitot tube performs an adequate measurement, it is important that it is aligned with the longitudinal axis of the aircraft, as we can see in this example. And also, it must be located in a part where the airflow is free from any interference. Because, when an aircraft moves through the airflow is altered by the parts of the plane, like for example the propeller or the wings. And this interfering flow is not suitable for measuring the total pressure. Therefore, the Pitot tube should be located in such a way that it is exposed to the proper airflow, in other words, the free airflow. However, a problem with this design is that being an object exposed to airflow, it is also susceptible to icing, which can block the main intake hole and thus produce errors in pressure measurement. So, in order to solve this problem, the Pitot tube incorporates a heating system which consists of electrical resistances that when they are turned on from the cockpit, make the tube heat up and melt any ice that may clog the tube. The switch by which this heating system is turned on is usually marked as Pitot heat and is located near the light switches. Now, another component of the Pitot tube is the drain hole. This is a small hole in the back of the tube that allows water to be removed from the system in case of flying in rainy conditions or when melting ice using the Pitot heat. As we can see, this Pitot tube is designed to eliminate any possible error in the pressure measurement. However, there are some errors that cannot be eliminated, the so-called position errors. The thing is that when flying at high angles of attack, the airflow that hits the aircraft is not parallel to the longitudinal axis, which also means that it is not parallel to the Pitot tube. Let's see this through an example. When we fly at low angles of attack, we can see that the airflow is practically aligned with the Pitot tube, which allows obtaining a fairly adequate total pressure measurement. However, if we fly at a high angle of attack, we can see that the airflow is no longer aligned with the Pitot tube. This generates slight errors in the measurement of total pressure. These errors are taken into account by the manufacturer in different configurations and speeds to publish a correction table in the aircraft manual. In this case, this calibration table corresponds to the airspeed indicator, since it is the only instrument to which the Pitot tube is connected. However, we will see this a little more in detail in the specific video about the airspeed indicator. But in summary, we must bear in mind that we are going to have slight errors in the indication of airspeed when performing maneuvers such as slow flight, flying in gusty or turbulent conditions, or when using flaps or slats. With this being said, we finish with the Pitot tube cover. It is important to keep the system free of dirt, insects and water. So on the ground, a cover is used for this tube that is normally brightly colored and has the inscription "Remove before flight," just to remind the pilot to remove this cover before flying, since otherwise there won't be any airspeed reading. Let's now move on with the other component of the system, the static port. This consists of a small hole normally located on the side of the fuselage, and it measures the air static pressure, or in other words, the atmospheric pressure. This static port is located in such a way that only the static pressure is allowed to enter and not the dynamic pressure. Let's see how this is achieved. Normally, this port is located on one side of the fuselage where a precise pressure value can be obtained. As we know, the static pressure is exerted in all directions, while the dynamic pressure is exerted only in the opposite direction to the plane's path. With this design, we can see that in the static port only enters the static pressure and not the dynamic, thus obtaining an adequate measurement. However, this design also has some position errors. If the aircraft performs a skid or a slide, part of the dynamic pressure will enter the static port, thus producing errors in the measurement. This occurs because in a skid or slide, the airflow not only hits the plane from the front, but slightly on one side. If we look at the previous example, but now making a skid, we can see the following. The static pressure will not change, however, the dynamic pressure will now be exerted slightly against the fuselage where the static port is located, which results in that part of that dynamic pressure will enter the static port. Apart from this effect, the use of flaps, slats, landing gear, or other parts of the plane can also cause changes in the local static pressure, so this effect must also be taken into account in the correction tables. In this case we have a correction table for the airspeed indicator and other for the altimeter. Since, as we will remember, the static port provides information to the three instruments. Now, as we will remember, the Pitot tube had a heating system that prevented it from being blocked by ice, so the question now is, what happens if the static port gets blocked? Well, for this case, we have an alternate static source, which is basically an additional static port that is connected to the system and can be activated by means of a switch in the cockpit. However, this alternate static port has a peculiarity, and it is that it is normally located inside the cabin to avoid a potential blockage due to external conditions. In principle, this is a pretty good design. However, the problem is that the static pressure measured inside the cabin is slightly different from the exterior static pressure, so then we will have a slight error in the measurement. This error is taken into account in the calibration tables. However, make sure that the calibration table you are using is for alternate static source instead of the normal one. With this, we have already seen all the information about the static port. One thing to finish is that, in multi-engine aircraft, it is common to find two independent Pitot static systems, one for the pilot's instruments and the other for the copilot's instruments. This design is quite beneficial as it reduces measurement errors and provides redundancy, since the instruments on one side can be compared with those on the other side to check how much difference they have or if some kind of problem is occurring. This procedure is known as a cross-check. I hope the information presented in this video has been useful. If so, don't forget to share, like, subscribe and leave a comment down below. Thank you for watching.